Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right. Hello,
welcome,
everybody.
Everyone. Welcome. Our colleagues are exiting the room as we speak.
If you hear it,
if you hear the doors and chatter from people who don't belong here, those are our amazing colleagues who doesn't get the memo that it's live stream time.
Yeah, we're in an office, and this is actually a conference room. So
Don't kill the mystery. We're in a blue magical space. We're surrounded by outer space and crazy.
That's not inaccurate. We are in
See?
space. We are in
Technically in
space.
some amount of space.
In some amount of space.
Yeah, yeah, exactly. That's a very fun way of putting it.
Yeah. Well, welcome everybody to another episode of Ask Us Anything about electrochemistry. For those of you who may or may not know, yesterday I did a webinar on voltammetry. It was part 1 of the webinar series. So thank you to all of those who joined. Of course, I ran a short Q&A during that time, but of course, if there are questions about that that webinar series, people can absolutely ask questions about it.
As always, I will share the tab for those as I tried to do, but didn't get it quick enough. But here's the tab of the webinar.
Oh, yes. Yeah.
So these are the voltammetry series. So part 1, you missed it. It's too late, but you can click on these buttons here. And this takes you to the YouTube link where you can watch the replay if you would like, if you missed it.
Yep.
They are on YouTube. They will be there for a little bit, and then they will be joining our tier 2 member only webinar playlist with the rest of these webinars that we've done in the past, all this never ending list. And next Thursday, here's part 2. So join.
Yep.
Alex is going to talk about kinetics and mass transport, whatever the heck that means.
Yeah.
And so join. You can register here, and there'll be the links to LinkedIn or YouTube. So join us for the webinar, for the voltammetry series.
Yes. Thank you. Looks like we have a question, which is good.
That is good. That's what we're here for.
Good. That's what we're here for.
That is it. So Andrew says, when you do a 2-electrode CV and one electrode is an alloy, 2 metals, and the other electrode is pure metal, how does the potentiostat know whether to measure the potential of metal 1 or metal 1 or 2 in alloy versus pure metal? It doesn't. The potentiostat doesn't, quote unquote, know anything. The potential that is measured and is a result of thermodynamics. So your alloy, that's part metal 1 and part 2, in the absence of any other complicated kinds of, I don't know, things that happen with alloys like this, like if you pick like nickel and copper together, right? That's like a monel, or maybe brass or something is some mixture of copper and iron and nickel, things like that, right? I don't know if there's some ways that they make a mixed lattice electrochemistry, but for the sake of argument, you could just say like there's nickel electrochemistry and there's copper electrochemistry, and there's iron electrochemistry, whatever the case may be, right? So or steel is a good example of that, right? Steel is mostly iron with a lot of other sort of 5% and under of other different elements, right? And a very simple assumption is to just kind of take whatever electrochemical processes might be happening with each of those metals in your alloy. There will be some equilibrium potential that will be reached that takes into account all of the different possible redox processes that can occur. And so that will, on balance, reach some equilibrium. Now, there's probably, some theoretical chemistry and physics or whatever is the right discipline that you could, in theory, I suppose, calculate like what that might be. But the reality is it's most often just measured. Like you put your, electrode into a solution and you get the potential that you observe, for example. But the potentiostat doesn't know, right? It doesn't know to measure nickel and ignore copper or vice versa or anything like that. That's not possible. It isn't even really physically possible.
Yeah.
Whether it's 2 electrode or 3 electrode, to be fair, right?
Yeah, that's right.
With a 2 electrode, as you've sort of indicated here, it's even more murky. But let's just say you had a 3 electrode system and you had a reference electrode of known, a known reference point, like a silver chloride or something like that. Well, you're still going to get some potential of the alloy, and it's just some, like I said, thermodynamic balance or whatever of the elements and the materials that are present in that alloy. The trickiest thing, of course, is with a 2 electrode system that we talk about often. Is batteries and electrolyzers, fuel cells, things of that nature. But very often the trouble is that if you have 1 volt or half a volt or whatever, or let's just say you go like do a CV from 1 volt to 500 millivolts, you changed by 500 millivolts. Well, did the working electrode, your alloy in this case, decrease its potential, like its electrochemical potential, so to speak, by 500 millivolts, and the counter electrode stayed exactly where it was? Or did the working electrode decrease by 250 and the counter electrode increased by 250, so that the difference is 500 now, right? Or was it 300, 200, or 400, 100, 600 minus 100? Like, you know what I mean? You don't know. And that's the tricky part about a 2 electrode system, because in particular, I would imagine with an alloy, it could be pretty murky because there's like more metals, more elements present. So what might be happening? What combination of electrochemical processes could be occurring on one or both species that are present that could be resulting in the potential changing? All of these are very big questions that are hard to know the answer to. But the main point is that the potentiostat does not know any of that. It is just measuring and then applying what you told it to apply. That's it, right? There's no real knowledge of that. That's why, as researchers, electrochemists, our job is to know the thing. The potentiostat's just a tool, right? It's a very fancy, very expensive tool, but it's just a tool. You're the intelligent brain behind your research. I hope, maybe AI is taking your job and you're not intelligent. I don't know, but I assume that you're the intelligent one. So hopefully that's the case. I don't know if you need to add anything to that. I sort of encroached on your territory because I'm talking about the Nernst equation.
You're getting dangerously close to talk. And you mentioned it first. You also mentioned it first.
I did that. That gives you full you are clear. You can talk about it for the next hour. Like it's a free Nernst webinar.
I did get my fill of the Nernst equation yesterday.
Derived it.
I derived it,
it's incredible.
which is good. No, Neil, I think you're right. So yes, absolutely. The potentiostat does not know what And actually, I talked a little bit about this yesterday. And I do see that there are other questions coming in, but we will get to it. People can see my okay.
You're good.
So one thing I talked about this yesterday. This may be helpful, but if you do have kind of 2 electrodes in solution, I'm not drawing these electrodes very well, and I have a voltmeter between the 2 of them, and then let's say I got like metal, and then I got alloy. I'll just use this part of the thing there.
It looks like a cool logo, like LA.
Oh yeah, that's right.
Like at the Los Angeles Lakers had a fancy logo for a metal electrode. That's what they would use.
That's what they would use.
Anyway, sorry, go ahead.
But okay, so if I have this system, that's what you're trying to measure, what the potential is. So the potential that gets measured, and actually, let me move this over so that it's a little bit easier to see. But what we measure, the voltage that's measured, is a combination of things. It's the potential of the alloy minus the potential of the solution minus, I didn't talk about this yesterday, there's a little IR compensate, drop, minus, and then it's the potential of the metal minus the potential of the solution. So that's what I know, I'm sorry because I didn't draw this all the way out, but like this is effectively negligible because the current's really, really low. The solution potentials tend to cross out, and this is what you end up getting. Of course, if the solution was different, then you have some other thing. But I think about metal alloys as like you have a lattice of multiple different metals in your system, and some are like the big one, and some are like maybe smaller, and you have this lattice, and this just changes the electronic properties. It changes where this phi A exists versus where this phi M exists. Because I think, and Neil's right, there's like the chemistry itself that governs where these things are. But if the solution is the same between both of them, then the solution potentials will cancel out. So if you had a redox molecule in the system, the potential difference that you're looking at would not include that redox couple in terms of the measurement. So that's my 2 cents. I know that there's some other questions that are coming in, so I want to get to those. But Andrew, I hope that answers your question or provides a little bit more information or clarification. And Shajil, we do see we will answer. I say that we answer all of Shajil's questions. We will get to his questions because he asked them much earlier in the live stream. So we'll get to those. Next though is TT. TT, good to see you coming back. I want to make sure that sometimes YouTube rearrange, or sometimes the streaming software we're using rearranges the list of questions. But your first question is, does it matter if in the equivalent circuit the solution resistance connected in series to the Warburg and the RCT, which are in parallel to the CPE, and if it's connected in series to CPE and Warburg plus RCT in parallel, does it make a change? Let me
draw something, TT, and tell me if this is. I think I
Yeah.
understand what you mean, and I think if it is, I know the answer. But are you saying what is the difference between, let's just say this? I want whether it's Warburg open, short, or any otherwise. Just forget about that. I'll put a CPE. It could be a capacitor, but let's just put a CPE here. Okay, so this is circuit 1, let's say, versus circuit Q. Warburg by itself. So can you tell me if this is what you're referring to? I want to see which one you were referring to being by itself. You're talking about the CP, maybe you're talking, essentially it's like one of them being by itself or in parallel or part of the circuit, something like that. I'm not sure if what I drew, the 2 different ones, is exactly your question or the 2 different circuits that you are referring to. I'll talk about this one just for a moment while I wait and see if you clarify if I've understood, because this is actually a kind of an important distinction though. And whether this is exactly your question, TT, I think this is something worth talking about, because there are let's just say historically, this one here on the left has been this is the Randles circuit. Okay, typically with an infinite Warburg, but could be a finite Warburg as well. This is the Randles circuit. This was the model proposed by Randles, I don't know, 60 years ago or 40 years ago, a long time ago, right? In more recent years, many people have been using this model, okay? And what I want to do is draw your attention to, first, a paper by someone who ought to be considered when it comes to this kind of thing.
Oh, this is the Orison paper.
The Orison paper.
Yes.
So this is a critical thing. And I recently had a.
Do you want to? Are you?
I'm going to in a moment. Okay. Yeah. I was just making sure it's the right paper.
Yep.
That's all.
Yeah.
Good call. So to that point here, this is a recent publication by Mark Orison. So I meant at the lower branch of the. Okay, I'm going to talk through this real quick, TT, because I'm sort of in it now, and it's an important point, and then I'll try to respond to what you're saying. To the point of this, this is a paper by Mark Orison, professor at the University of Florida, and on the proper use of Warburg impedance. Okay, and so he basically brings up this point that there are these two models, specifically where the Warburg is dissociated, or when it's as Randles put it. Okay, the long and short is that most of the time, this is the correct model. Okay. With the Warburg embedded within the RC. The model, again, I'll just share my slides again. The model.
And he does actually have a clarifying point about this.
I did see that. I'm just going to finish this and then we'll talk about it. It's relatively quick here. This one is correct. In some cases, researchers, let's just say, get away with it using this one for a couple of reasons. One is that under certain circumstances, these models actually converge and they're basically the same. Another reason why apparently people like to use this model is for in situations where you might have, for instance, multiple RQs, okay? And so what happens here, so this would be Q2, Q1, whatever. So there's multiple charge transfer processes. Some people have taken the approach, well, I don't know, should the Warburg, okay, well, if I want to make this embedded, fine. Should it go in here or should it go in here? And I don't know which one it should go in, right? I'm confused. So instead, I'm just going to abstract it and put it by itself. And my contention to that is that the fact that you don't know which one it should go in doesn't mean it shouldn't go in one of them. It just means you don't know. So it might require trial and error. But I reject the idea that I don't know which of the, RQ void elements or whatever should be a Randles element. So I'm not going to put it in either of them is not an acceptable answer. That just means that, okay, so you might figure it out. That's what research is. It doesn't make this necessarily correct. Okay. And mainly the reason is that, under circumstances with very fast kinetics or very small time constants, these models are roughly equivalent. Under most circumstances, that is not the case, especially when Warburg is concerned. And especially when it comes to batteries and things of that nature, which have very high capacitances, often high currents, and long time constants. It is not the same and it is not applicable. And so this is not actually technically mathematically correct. You want to use this model. The models do not converge when you have any appreciable amount of capacitance, current, or time constants. They are not the same mathematically, and so it is more correct to have it embedded. Again, with fast kinetics or small RC values, the models can be roughly equivalent. But when that's not the case, it's most appropriate to use the other one. So let me move on now. That was kind of a point of clarification that I did webinars previously. I used to say, I don't know which one's right. I'm going to use this one, but I guess you could use either. And then literally that paper was published, I think last year or 2 years ago. It's a relatively, and I started correcting myself in newer versions of my own webinar to say, actually, I've seen the light. Here's the reason, right? So TT could clarify. I meant if the lower branch of the first left model was switched with the upper one. And yes, I wanted to ask if the right one indeed differs from the left. Okay, so I covered the second question, which is what if the right one. But you're saying, what if the lower branch of the left first model switched with the upper one?
I think it's the idea that just like you have these parallel things and then you just switch whether one's on top or one's on the bottom.
So you're saying if the resistor is up here.
Oh, is he saying if there's a resistors up there or if that whole part? Because he's been saying resistor RCT plus Warburg and Warburg, RCT plus Warburg moving like together
So are you? Yeah.
in
So
each one.
so tell me, are you saying this, or are you saying I should start a new slide?
You can get rid of the
Yeah,
yeah.
I'm just gonna.
Yeah, you can copy.
That's what I was gonna do. Yeah, lasso this thing, bring it over. So you're saying, for example, this, or are you saying, like if I just flip it, for example, like if I do, sorry, that would be the Q. I'm not gonna hit Q, undo.
Yeah, you can. That's a good cue.
So are you? It's a great cue.
It's a great cue.
Okay, so are you saying like if all I did was flip these? I mean, literally all I did was draw the resistor in the Warburg on top and the Q on the bottom. There's no difference between this model right here and what I drew in the previous slide. They're mathematically equivalent. The fact that one's on the top and one's on the bottom is irrelevant. They're both in parallel. If you're referring to something like this here, this is, it's not mathematically the same.
And physically, it wouldn't represent something that's true.
They could, for example, Q, this Q has an alpha, and this Warburg, if this is an infinite, is essentially alpha equals 0.5. If it just so happens that you have an alpha here equal to 0.5 as well, because it's quite non-ideal, they might coincidentally be the same, but there's nothing about these that would be the same. In this case, what you're saying, I mean, it's just not even physically the same. Like you're talking about a resistor in parallel with the diffusional component, and it's just not really,
it doesn't represent reality.
It doesn't represent. Yeah, it's just not how it's not how we conceptualize. The electrode, and then electrons transferring one way or the other. The electrons are transferring in parallel with a double layer capacitance. Basically, we sort of conceptualize it that way. This always kind of trips you up because you'd be like, well, look, it looks like it's in series because one's happening and the other's happening. I know sometimes I find it hard to draw and talk about what's in series and what's in parallel. So admittedly, I'm not sure I'm perfectly adept at like drawing it and then saying, of course, this is in parallel. And of course, this is fair enough. Maybe the best way to think about it is that if I draw it sideways, for instance, we think about it in parallel because while simultaneously electron can transfer in one direction or another, there is a double layer. And so it's like, it's a parallel thing because we can have charge transfer at this surface. We can also have capacitance at this surface. And so they can happen at the same time on the same surface. So that's why we think of them in parallel. Diffusion, I mean, again, it's like you could think about diffusion. Well, diffusion is happening, so why wouldn't the diffusion be here, like also in parallel? Okay, we don't do that. It's sort of in parallel because it's also here. So it's in parallel with the capacitance. I know this is kind of getting murky here, like why is it where or whatever. The other way to sort of convince yourself, which is a less satisfying answer, but it's technically true, is that look, if you're not convinced, why can't the Warburg be down here? Why isn't this model? Make it and see what it looks like. Like I can do that for you. We could just do that for a second.
Yeah. He's just talking about, it turns out he's just talking about switching RCT and Warburg up and down. It just sounds like it's just a convention of circuits that, like, when you have two things that are in parallel, in this particular case, you can flip them and they're exactly equivalent. There's no difference.
Oh, yeah. If you're talking about, yeah. So in some sense, you're talking about like, let's show.
Yeah, if you go back to your,
I'm just going to go to Aftermath and show. Actually, we'll have to share the full screen because you won't see the window.
Yeah.
It's like there's a pop-up for the thing, right? So it won't show. So, okay. So if I do I'll just try to draw it for a second to show you. Yeah, I think what you're referring to is actually quite simple. You're just, there's a complete equivalence here. So if I have this, and then I have a CPE by itself, and I have an R and a W connected, right? And I have it like this, or I have it like this. I could put these down here, whatever. That's exactly the same. There's no difference. Mathematically, it's exactly the same. It's like these are in parallel. The Q and the R2W1 here. These are in parallel. Whether the Q is below it physically or not. Oops, just trying to move this up.
Mhm.
It makes there's absolutely no difference. Mathematically, it's the exact same thing. Because technically, like you could just draw the line. Like the line from the resistor R1 here can go to the R2 or to the Q. And if the Q is up here and the R is down here or whatever, it makes absolutely no difference. In fact, this R could also be on this side. I'm going to blow your mind even more, right? This R could be over here. Oh my gosh, the IR compensation is happening afterwards. How is that even possible? There's no difference. It's mathematically the same. We just tend to draw it over here.
Yeah,
disconnected.
that's also true.
This is mathematically exactly the same. There's no difference here. Just no one in their ever loving mind would draw it this way because everyone would be like, "What are you doing? It looks weird." But in fact, I could even invert this now and it would draw the same. It's exactly the same.
Mm-hmm.
So that's like Kirchhoff's laws physics. That's just a physics thing, circuitry.
Mm-hmm.
It's like adding units in parallel and in series or whatever. That can be in any order. Makes no difference. And this is back to one of all their main sort of endless hearkening on points that I tend to give when I give my impedance webinars, which is we tend to put first semicircle, first RQ, second semicircle, second RQ, and we line them up kind of like in order, quote unquote, by what we see, because it makes our brains feel better. The reality is that everything is happening at the same time, just at different speeds.
Yeah,
right.
Right.
And so it's a fallacy to assume that what you see in the impedance data is the order it happens in real life. That's not true. It's the speed. Like now, if one of them is so much faster or slower, you might think of it as happening first and second, but they're technically happening all at the same time. Just some of them are happening faster than the others. The ones that happen faster appear first, but mathematically, it's all the same. It's all the same. You can move things around. It makes no difference. You can't mix up like the Q and the thing, like those flipping completely, like the Q going down here and the W up here, like the way I drew. Apparently, I don't think that's what you were asking, but that's different. But hopefully you can see that mathematically adding things in series, R plus, like 1 plus 2 is the same as 2 plus 1, right? That's just math. So it's less to do with electrochemistry and more just simple math.
Yeah.
All right, let's move on.
Yeah. So we'll get to TT's other question later. We do have a question from Shajil. He has actually 4 questions. And all these questions are kind of interspersed. So yes, we do remember you from last week. Yeah, it was last week.
I think it was last week.
Can you explain what are included in the Warburg region? Is it only ion diffusion or even the electron? And I think some of his other questions are related to this, because his other questions about is the Warburg diffusion, is the diffusion of ions from the bulk to the electrode surface, or does it include diffusion of it through the electrode pores, like a solid state diffusion? And then his other questions are a little more. We should get to some other people's questions first before we answer like questions 3 and 4. But so I think it's important to recognize, like, okay, the Warburg region is this low frequency region in the Nyquist plot, and that's just the time scale of when diffusion happens. So in the case of, is it ion diffusion or electron diffusion? It is ion diffusion. Electron transfer happens very, very quickly.
Electrons don't diffuse.
Yeah, they don't also diffuse as well.
Yeah, that's not really exactly right. So
yeah, so it is ion diffusion. Now, this is also in a relatively simple, like 3 electrode solution phase thing, because you can get things like mid to low frequency inductance and random stuff like that. These, I know. It's like I get to say my favorite thing. I get to say my least favorite thing.
Oh, this is a fun day.
You can get these inductive loops as well, which I actually don't know enough about, like what causes inductive loops and things like that. But as it pertains to Warburg and diffusion, we're only talking about ions, specifically molecules in solution, which can be ions, diffusing through the electrode electrolyte interface, sort of say. His question 2, which is related to this, is Warburg diffusion the diffusion of ions from the bulk to the electrode surface? I guess he's also wondering if it can
Could
be
be
like
either.
the opposite way.
Could be either.
But yeah,
Warburg is definitionally the impedance of diffusion. That's it.
yes.
So that
Yeah.
could be semi-infinite diffusion from the bulk to the surface, from the surface to the bulk, ions moving through what's called the diffusion layer. So at some point, they're sort of beyond detectability. You know, we talk about inner and outer Helmholtz plane and diffuse regions and all kinds of stuff, right? But to some degree, the measurable movement of ions, which is charge, but it's not electrons, it's ions, right? Moving in solution at some distance from the electrode surface to the electrode or from the electrode. That has an impedance associated with it. That's what the Warburg is measuring. Whether it is in pores or through a fixed boundary length or through the microstructure of the membrane of the electrode itself, of something like that, simply impacts the kind of Warburg element you would use. For instance, a Warburg finite Warburg, Warburg open, Warburg short, or a Warburg infinite, which is the most common one with the 45-degree line. But all of those are classified as diffusion, and all of those are classified as Warburg. It's just different types of them. So actually all of them are included in different types of Warburg elements and Warburg processes. So that's all. Those are all there.
Yeah.
I guess you'd say.
Yeah. Yeah.
So should we move to other people's questions?
Yeah, we'll move to other people's questions, because then we will also talk more about, I think there's actually a few questions actually about Warburg impedance and stuff as we continue. TT asks, what would be the reason for having 2 semicircles? Does it only happen if I have 2 different materials? So it's 2 different interfaces where each has its own charge transfer resistance? Question mark.
That's a possibility.
That is a possibility. I think in general, just from a fundamental impedance thing, is that you can clearly identify 2 different processes that have 2 different time constants. You can say that with certainty, with a large degree of certainty. They have 2 different time constants. Where they come from, could you have more things happening? Yeah, you can. If you have multiple processes, but some of them have the same time constants, you wouldn't be able to easily deconvolute them.
Right.
But that is what it means fundamentally if you see 2 semicircles.
And very often it's possible to come from what you've identified, which is to say you have 2 materials. You have like a substrate and a film. So you have an interface, some resistance and some capacitive effect between the substrate and the film. And then you have a second interface between the film and the electrolyte, for instance. So you have 2 interfaces, 2 time constants, 2 processes that can occur, right? So there you go. That could lead to 2 semicircles. But it could also be 2 different processes on the same surface that just happen to occur at different speeds. Like Alex said, they're just 2 different time constants. There's just 2 different processes on the same metal surface that can also happen. Yeah.
And it may even be the case that they may have their own charge transfer resistance, but they may also have their own like capacitance. So those values can also be different. So in addition to charge transfer, consider the capacitance at that interface that would also cause the semicircle.
Yes.
Yeah.
Okay. So I think Jesse is next.
Yes, Jesse Mentor is next.
So Jesse has asked, for ions, what is the difference between migration of ions and the diffusion of ions? I thought they were the same.
Good question. And it's just funny because a little bit we'll talk a little bit about this too, because Shajil's 4th question is actually about the difference between migration, diffusion, and convection.
Well, there
which
you go.
We'll get to.
So we'll answer these in one fell swoop, I
guess.
Yeah,
we'll kind of talk about the subject sort of in one fell swoop. So migration is the movement of ions as the effect of an electric field. So you have an electric field, some gradient. You have maybe some plus charged ions. The positively charged ions will move closer to the negatively charged area of the electric field, or they'll get repelled from the positively charged area of the electric field. So they move in accordance to an electric field. So that's what migration is of an ion. Diffusion is just basically it's the absence of that electric field. I like to think of it as the random motion of molecules. It's sometimes defined as the movement of ions or as the result of a concentration gradient. That's another like definition of it. So that is, and actually I need to think more about my whole like.
I have to change our background.
Oh, you have to, yeah. I'm thinking about this more because the whole like electrochemical potential thing creates a thermodynamic reason why ions can or why molecules would move as a result of concentration gradients, because it would actually give a reason thermodynamically why a molecule would move. So
But that still doesn't explain diffusion specifically.
Diffusion
as a concept.
as a concept.
So you would say concentration gradients and diffusion being the connected things.
Yes.
So what you just described is more about thermodynamics and a driving force, let's say, induced by electrochemical potential differences. That all tracks. That is, and I could be off here, but my impression, thinking about like the famous diagram of the field changing from phi m to phi s, for instance, that's still kind of in line with migration.
Yeah,
it's a migration, right? Like unless there's something that is incorrect about this assumption in this definition, diffusion as one of the three pillars of the way things move, right? Migration, diffusion, and convection. Diffusion is definitionally random. If it is random, it is not guided by outside forces. That is, it cannot be both of those things.
Yeah, that's right.
It is either you can't be a married bachelor, right?
Yeah,
okay,
that's right.
If it is random, you can't have a random number generator that also likes the number 12.
That's a good point.
Okay,
I didn't think about.
So you're not. I think I don't question yourself. This is still correct, even if it trips people up and drives people nuts. I don't care. I will defend it to the death.
Yeah.
Technically, if it is random, then it's still valid.
Then it's still valid.
You're probably right that there's other forces and driving forces, migration and electrochemical potential and gradients and field effects. Maybe in a metal it's less, but through the solution, okay, fine. Like there's potential driving forces that cause ions to move, but diffusion is not one of them.
Yeah.
Right.
Yeah. And diffusion is, just as Neil said, it's the random motion of molecules. It's often even modeled as a random walk. Right. Literally, if you have something at this one point, it has a 50% chance to move this way and a 50% chance to move this way. And you can even model that, like, statistically at this point, there's like a 0.16% probability the molecule will be right here, because it started here and then it has 50, 50, 50, and it keeps going down all the way until that fraction is like 0.1 or 0.001 or something like that. But it is random motion, a probability of things. And the way I like to think about diffusion, because diffusion is often reported as like a diffusion coefficient, is in like how far does the molecule move or travel per unit time. And it's usually defined as like a root mean square. So it's really like a statistical average of like where the molecule is going to be. So one is electric field movement, migration. The other one is random motion, Brownian motion. That's what diffusion is. So Jesse, I hope that helps and answer stuff.
Shujil, I think his question was right. Yeah. Same thing.
Yeah. Same thing. Question 4.
Convection, forced movement.
Yeah. Convection is just in simple terms. Yeah. It's forced movement. It's sometimes described. So if you look at like mathematical equations that describe convection, there will be a velocity component. Like it's just like physical macroscopic movement. Stirring is the easiest example. A propeller.
A pump.
Yeah.
Something that forces. Molecules are going to randomly move left or right, but if you're pushing them left, they're going to move left.
They're all moving left.
Right. In simple terms, you can think of it that way.
Yeah. So then we can go to Shajil's third question, because that's a little different. So since the solid state diffusion and bulk diffusion are taking place with different Wait, so
Yeah, don't confuse diffusion with kinetics.
yeah.
Can we deconvolute this Warburg through some function like Fourier transform? So kinetics is the speed at which a reaction occurs. Diffusion is not a reaction occurring. So you're mixing concepts, I think. You can talk about this. I suppose you could talk about, in some sense, the speed at which things are diffusing or moving. You know, the extent to which diffusion is taking place. I'm trying to use other words here, and apologies if English isn't maybe the most convenient language for this kind of what I would call a semantic discussion. But like, there's a reason why different things have different Warburg impedances. They're not all the same. So the way in which diffusion occurs can be different. So you might say it's faster or slower, better, worse, like whatever the word we want to use is. But kinetics is specifically the speed of an electron transfer. That is what kinetics means. So if you're thinking about analyzing the diffusion through the lens of kinetics, I don't believe that's applicable. You don't want to mix those concepts. Those are sort of separate things that are happening at the same time. Diffusion is occurring, mass transport is occurring, and kinetics is occurring. If there's a redox process, let's say, occurring, electron is going from one species to another, to the electrode from the whatever, right? Electrons are moving, but that's separate from diffusion. Whether the diffusion is happening fast or slow, ionic movement is not kinetics. It's not the same thing.
Yeah. That's right.
So don't mix up those things. And then, as a general rule, can we deconvolute Warburg through Fourier transform? Warburg is definitionally an impedance that is interrogated through an impedance experiment, which is where you apply a sine wave, which is deconvoluted via Fourier transform.
Yeah, that's right.
Discrete Fourier transform or fast Fourier transform. So yes, in fact, that's exactly how you get your Warburg impedance in the first place, is through a Fourier transform of sinusoidal perturbation. So you could go backwards. You could retrieve the raw signals. For example, you have the Warburg impedance. You could look at the raw signals, and then you could do Fourier transform to obtain the Warburg. But if you're looking at impedance data, you're already looking at the deconvoluted. The Warburg data, the impedance data, the Nyquist plot, the Bode plot, that is already the deconvoluted via Fourier transform data.
Yeah.
You're actually already doing that.
Maybe
you haven't thought about it that way, but that's exactly what you're doing, because the raw signal is a sine wave of current and potential.
Yeah. And the sine wave is oscillating as a function of time.
Yes.
And we are now looking at something as a function of frequency. So we've taken the Fourier transform, it inverts the time element. And so that's what we're looking at. We know more about the frequency with which impedance, Warburg impedance occurs at. So yeah.
So he means the time constant for diffusion.
Oh.
That is,
it's weird.
I'm not sure diffusion has an associative time constant per se.
Or if it does, it would be very broad. So like,
how you even calculate it, to be honest, because the unit is square root of time. Like there isn't, you know what I mean? Like R times C, a resistor like ohms times farads equals seconds, like dimensionally.
Yeah, dimensionally.
Which is even if you forget about why, you could think about it like physically. It's the way we say it. Apologies if this doesn't make any sense to you. Is like the time it takes to charge the capacitor through this resistor. They're in parallel, but that's kind of the way we say it, and so it's a time element to that. But mathematically, R times C is seconds. Ohms times farads is dimensional analysis gives you seconds. So from a Warburg perspective, there's no time as one of the, for example, like fitted parameters. It's technically like ohms per square root of second or square root of second per ohms. It depends on how you represent it. There actually is no time variable extracted, or if there is, I'm not aware exactly how that's done. That's not exactly the right application, I would say. So anyway,
he's got a few more questions. We can dive a little bit more. Do you have your slides?
Yes.
On just the
Warburg?
calculation of the diffusion coefficient from
from Warburg.
From Warburg,
Yeah.
because he is asking a little bit about like the study of the diffusion coefficient through EIS, the Warburg tail, which we have slides. We have Neil has a full-on webinar on the subject if you want more of that. It's one of our archived webinars.
Yeah, so
we can talk
I'll just show you the slides
about
briefly, but yeah, these are the slides that I have on calculating the diffusion coefficient from the Warburg. So for instance, the impedance to Warburg, and actually this is just this last question from Shajil here, more in line of the same thing. How fast the bulk diffusion through the pores, can we know how fast one is compared to the other? Again, the word, whatever you want to say, how fast the diffusion is, how good or bad the diffusion is, whatever you want to say, the simplest way to sort of think about that is just through the impedance. So a higher impedance usually means the process is worse, generally speaking. Let's just sort of broadly say something like that. If the Warburg impedance of material A is 1,000 ohms and the Warburg impedance of material B is 100 ohms, we would say that the diffusion is worse for A. It's higher impedance. It's like V, you think V is IR, like the higher the impedance, the lower the current I can get out of it. The worse its performance, so to speak, right? Like generally speaking. So whether that means that the diffusion is faster or slower, or it's choked because of geometry, or the electrolyte concentration is of something, like I don't know exactly how that can be defined per se for each set of circumstances, but if you're talking about better and worse, you can simply look at the impedance of the Warburg element of each of them. You could look at that. Perhaps you could see, even just statistically, it's the ZW here, but it's also proportionate to the W. So you could look at the Warburg constant, for instance, and if the Warburg constant is in the numerator, the way this is, it might be inverse. So you have to be careful what you're looking at. Some software have this in the denominator, so be careful. What I'm showing you is in the numerator. You could, for instance, say the bigger the Warburg constant, the bigger the Warburg impedance, and therefore the worse it is, worse, so to speak, whatever. The way that manifests on the Nyquist plot, for instance, is it's a longer tail. So your tail like this is whatever this W is, 2,000. So this is just an example of a number here, right? So if I had a W of 4,000, the tail would be like longer. So physically on the plot, if the tail goes off really long in comparison to the size of the semicircle, for instance, that's indicative of higher impedance Warburg. So worse diffusion, whatever words you want to say, slower, worse, bad, again, whatever the wording might be. Those are how you might interpret that. And then calculating the diffusion coefficient, there's a bit of a walkthrough here, but just loosely speaking, you can say it's something like this. You're using this expression through the Warburg impedance is equivalent to RT over n squared f squared A, and then you have basically the diffusion coefficient and the concentration of the species, the bulk in the bulk. This is for the most simple case, for instance. This is from Bard and Faulkner. Typically, you can extract the diffusion coefficient from this expression here if you know the Warburg constant from your fitting. So
another way that might be helpful, that has at least helped me with like conceptually understanding diffusion, is I think of it as the speed at which a molecule is moving. It's like diffusion coefficient is even in units of like distance per time,
or area per time,
or area per time, right? Because it's like a moving plane, one-dimensional plane. How we model it. So and when it comes to diffusion through, so when you have a higher impedance in the Warburg, it means that it's a slower process, because the time, which is the frequency with which that data point in the EIS was taken, it's taken at a specific frequency. It's a low frequency, but man, it's like it's a lot of resistance. Takes a lot of time and distance to actually get to that point. Right. So that's an indication of just like how fast does the molecule move. And physically, you can think of that as, if I have small molecules, they diffuse more quickly. It's easier if you're a small molecule to move around through different places. If you're a big molecule with like bulky ligands or sterically hindered, ligands or stuff like that, it's hard for that molecule to get from point A to point B. If the solvent that the molecule is diffusing through is also big and has some interesting random electrostatics, sort of say, that may also hinder how quickly the molecule moves or diffuses through that solution. The temperature can even be a factor. If you do this at one temperature versus another temperature, you can get a different diffusion coefficient or constant for that. When it comes through diffusion through pores, I like to think about. I have a video on this conceptual understanding of Warburg impedance, which is that if you're moving through, if something's diffusing through a pore, the diffusion that we're measuring, because this is electrochemistry, fundamentally an electron transfer has to be occurring. It's like we measure the electron transfer occurring, and the time it takes for the electron transfer to occur tells us something about diffusion at that time scale. So diffusion through a pore can give you, actually most of the time I think it gives you more information about the thickness of the, the size of the pore, the thickness of the layer. But it's about how easy, it's easy for the molecule to get from the bulk solution towards the electrode, or towards the porous surface, and then it's hard through the pores for it to get to the electrode to get an electron transfer. And that's where you get things like Warburg opens and Warburg shorts, where you start to see either the Warburg tail go up or the Warburg tail start to curve down, because through a pore, it's as if, that becomes like the limiting factor, and it's almost resistive on the time scale of moving charge back and forth through the pore. Well, there's almost an infinite amount of solution at a really, really slow time scale for you to get charge through the pores to the electrode to have an electron transfer. So it's tricky, Shajil. It's definitely very, very tricky, but hopefully some of these ideas kind of help with that. And I'm sure throughout this, just based on the questions, which I have to figure out where we're at again.
Yeah, I was looking back. I think Shajil actually had the next one in line here. After his question 4, he asked about, and he had some follow-up about symmetrical stuff. It's similar to this, but so some of it's CV, but there was some diffusional stuff. So first, why the CV of an electrode in a 2-electrode symmetric device is so different from the 3-electrode system with a reference and a counter. And I think there was a bit of follow-up. I mean, it's kind of more in the diffusional thing. I think the first answer to this has kind of already been discussed a bit ago.
Just with like measuring the potential.
I mean, I know you're talking about symmetrical cell, so the conventional wisdom would be like, well, they're the same, but that doesn't necessarily mean they have the same potential, especially if you're forcibly changing the potential. In general, you could imagine that the voltage of a symmetrical cell, when you're not doing anything, will be likely 0. Like if you have the exact same electrolyte contacting both sides, the exact same electrode, and in theory, the voltage between the two should be 0. But if you have a reference electrode, it need not be 0, because the reference electrode is now the reference point, and it has you're measuring with respect to the reference electrode. The other side of your symmetrical cell is acting like the counter electrode, in which case it is really not part. It's part of the circuit for completing the current path, but it's not part of what you're measuring. There's the fundamental difference of this. It leads into your next question about the symmetrical supercapacitor, things like that. One of the fundamental differences between a 2 and 3 electrode measurement, whether it's CV or impedance or anything else, is that when you are doing a 3 electrode measurement, your current and potential are direct measurements of the working electrode only. Now, the current is also equal and opposite to the counter electrode, but the counter electrode's potential need not be the equal and opposite potential. You don't know what it is. It could be anything. With a 2 electrode system, that is not the case. With a 2 electrode system, you are necessarily measuring both electrodes. Now, because the reference line the sense and the drive line are on the same counter electrode. So with a 2-electrode system, and this is one of the things with impedance, for instance, that can be tricky. For instance, if you're trying to isolate in a battery, for instance, the cathode or whatever, but you have a 2-electrode system, you cannot do so easily. You will get impedance results and electrochemical information from the cathode because it's a 2-electrode system and you're measuring the cathode just as much as the anode. If you can jam a reference electrode in there, you can isolate just the cathode, for instance, or just the anode. So that's why some people do that with batteries, is they try to get a reference somehow in their battery, so they can isolate measurements on one or the other, for instance, get the individual voltages or potentials of one electrode or the other as it charges, discharges, things of that nature. And again, it kind of leads into the next, I guess, kinds of questions. I'm trying to think. TT had a question in there, I think, and Tamogna had a bit about sending an LSV trace, so we can look at that. But
did you get the email?
No, I don't think so. I'm just saying
okay.
if we do get it, we can
okay.
try to see. But this is more about the CV with 2 electrodes. Just think of a symmetric supercapacitor. The cations and ions or anions, I guess, are of different size, maybe different valency, so different solvent sphere. So they're moving with diffusion should be different. But in a symmetric device, they both appear in a single Warburg. Well, not necessarily. They might. You bring up a good point. It's like if there are different ions, different sized things, in theory, they could, as you said, right? Smaller things might diffuse faster, whatever. Like, okay, yeah. It's all relative here, right? I mean, again, the time constant, I just sort of talked openly about how you shouldn't talk about a time constant thing. Okay, but fine. But in a more broad sense, where something appears in the impedance data, whether you think about it in terms of a time constant or you just think about it in terms of the speed more broadly, if the difference between these different sized, different valence molecules or ions, yeah, there's differences, but maybe even despite those differences, the diffusional behavior is not different enough. They may blend together, and it may be difficult to deconvolute those effects. That's absolutely possible. All of the diffusion virtually, let's just say, might fall within a relatively narrow or some low frequency window such that you can't deconvolute between like the diffusion of the sulfate anions and the sodium cations. Like you might not be able to differentiate between those different ions diffusion via EIS. You just might not. And I don't know anybody that really has tried, for instance, to like put, let's just say, 2 Warburg elements and like try to fit 2 different discrete ones to capture each ion. I don't even know that that's physically possible, and I'm not sure that it is measurable.
I think another thing is in a 2-electrode system, it's like the current is, there's only one current. The current at the anode, cathode, or working encounter are the same. They're equal and opposite. So what happens sometimes in like CV experiments, like for example, you may do an experiment where in principle, no limitations, you should get like really high catalytic current, for example, on your working electrode. You have this awesome catalyst. But if the counter electrode can't keep up, then the amount of current is going to be limited by the charge that your counter electrode can hold. Similarly, if you think that you're going to get like diffusion or you're going to get more current on one electrode than another, because that's kind of what you're measuring. It's like the potential in the 2-electrode cell for EIS has the same current and the same voltage difference between these two electrodes. So what part of the current is like the counter electrode, what part is the working electrode? You have to use a 3-electrode system to kind of deconvolute those two things, if in fact the Warburg impedance is different. So I think in a 2-electrode system, you're not going to be able to deconvolute these 2 Warburg elements like accurately, sort of say. And then Shajil actually has a comment about this. So the apparent potential felt by the electrode is different in 2 and 3 electrodes. I would word it just a little differently. I would say the apparent potential is measured differently. It's like the potential itself in kind of absolute space is like at the same level, but where you're measuring it in a 2 versus 3 electrode system is going to be different, so it appears differently. Hopefully that kind of makes sense. That's one way to think about it.
Yeah, exactly.
Okay.
It's different.
Apparently it's different. Oh man, I forgot.
I know. I'm trying to find.
We're trying to figure out.
We've been jumping around.
We've been jumping around a little bit trying to.
I think TT had we covered TT.
We covered TT
stuff. 2 semicircles. We covered that, and we've been jumping around a lot. So let's see here. Tamogna had talked about that. Yeah, TT said this. What does the polarization effect mean? I read it in many CV interpretations, and they ascribed the CV curve's behavior to it and the good reversibility by shifting the peaks at different scan rate. Well, first of all, polarization is just a fancy way of saying changing the potential.
Yeah.
So I don't know if polarization effect is something else that's specific. Like if you read that, if that's a term that some people in the literature are using to refer to some other thing. I'm not sure. I don't know precisely what that means, to be honest. But again, when you talk about polarizing, sometimes we say we polarize the electrode. It just means you're changing the potential. It's just a very fancy way of saying
an old way of saying
that. Yeah, exactly. It's from the an early term for electrochemistry was polarography.
Yeah, polarography.
So we don't really say that anymore, but the word polarization has stuck. So
yeah, it also comes from like using mercury and stuff like that. There's all kinds of stuff like that. They're just not used today.
We don't use mercury anymore because we don't like dying.
Yes, or getting mercury poisoning, which leads to death.
Which leads to death.
So
we don't want to die, so we use carbon or something.
Yeah,
or platinum, whatever.
Oh, and cleaning techniques have gotten a lot better. They
have. This doesn't mean people do said cleaning techniques, but they have gotten better if you would like to do them. The second part of this question, I think, was good reversibility by shifting peaks at different scan rate. They ascribed the CV curve's behavior to it and the good reversibility by shifting the peaks at different. It almost sounds like you're talking in circles about a thing. So for example, if you do CVs at different scan rates and the peaks change or widen, it means there's a level of irreversibility or pseudo reversibility, in theory, and it almost never happens this way in perfect world, right? But let's just pretend in a perfect world with a perfectly reversible redox couple, if you increase the scan rate, the potential at which the peak occurs on both the positive and negative would remain exactly the same. It would get higher, the peak current would grow, but the peak potential would remain the same. In practicality, that almost never happens. It's really hard to make that exact. Like if you go from like 10 to like 300 millivolts per second or something, it'll look slightly separated. Nothing's behaves exactly perfectly. But it almost sounds like you were saying like shifting the peaks is good reversibility. Like I maybe again, something about this polarization effect, or there's something related there that I don't maybe quite understand what this term is referring to, but that's kind of the long and short of peaks in CV. Like again, if they're showing up here and here, and there's 60 millivolts in between them, and you start scanning faster and they start separating, it's pseudo reversible or moderate. It's not perfectly reversible. That's just kind of the.
Could also be solution resistance.
That's it. Yeah.
Too much solution.
Actually, that's probably the main reason why they even in a really well reversible system, they start to split a little because of IR compensation. The current's getting higher, so your effective IR drop gets worse.
It gets bigger.
Yeah, that's a good point. I always forget to say that.
Okay. Hob G has a question. I think he's next.
Yes, I think so.
How can diffusion be the random motion of molecules in a Randles-Sevcik equation? So one of the ways to let's bring up the Randles-Sevcik equation. Just so that we know everyone here is looking at stuff. So this is the Randles-Sevcik equation. This is the version of it at room temperature. It's a slightly simpler version. And it just describes that the peak current in a cyclic voltammogram is equal to all this stuff that also includes a diffusion coefficient. And so, how can it be? So, I guess your question is, how can diffusion be random motion of molecules in Randles-Sevcik equation? So, there's nothing. It has a diffusion coefficient in it, and the way the Randles-Sevcik, it makes it sound like, oh, it's a very reproducible thing. Like diffusion is random, so you should always get like a random result or something. I would say there is perhaps a predictability, if you will, because what we're dealing with in the Randles-Sevcik equation for cyclic voltammetry is like one dimension linear diffusion. So, the way we kind of think of this in like a cyclic voltammogram, actually, I will. It's easier to kind of have the electrode surface, is that molecules, there are molecules all over the place, right? And they're random and they're moving all over doing stuff. Well, and again, there's kind of one thing that's important to note. That I think there's also a scale, a magnitude of this that as humans, it's kind of hard for us to wrap our heads around it completely. But there's a lot of molecules here. There's like a ton of molecules that are right at the surface and they're moving randomly. And there's a lot of molecules here that are near the surface and they're moving randomly. The molecules that are like right here at the surface that can undergo an electron transfer when you're scanning in CV, they like very, very quickly convert to being the other form. But they're moving around randomly. They're moving this way, they're also moving that way. Well, some of these molecules here are also moving this way and that way and this way and that way. And the important thing about this is that in this one-dimensional diffusion, because you may think, oh, well, this molecule might just stay here. It might just stay right next to the electrode surface. And there's a good number of molecules that are doing that. But when you really have literally trillions upon trillions of molecules, even, a millimole, there's still a lot of them that are near the surface and going one way or another. And we need to think about like statistical averages when you really think about random motion in one direction, because if you really like look into the mathematics behind diffusion and random motion in one direction, if I have a molecule that's right here and it's got like a percent chance to move this way and that way, on average, after like a bajillion tries, you're gonna find it here. But it will have gone here, it will have gone here, it'll be here, 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 it'll be all these places in between. It will have moved in a certain period of time. So if you think about that, this is how we ultimately end up getting these concentration profiles. And really, one of the best ways to kind of showcase this is to I'm going to show something slightly different. I'm just going to show our aftermath software. So if you do simulation, which is something that we offer as a company, and if I simulate this, just a simple cyclic voltammogram, it's important to look at the concentration profile as a function of distance to the electrode. So while you're doing cyclic voltammetry, and eventually you start to reach the potential where these reactions occur, you notice that I still have this like bulk amount of stuff in the solution. But then when I get to the electrode surface, it starts to decrease. And I have this increase in, say, the concentration of the reduced species if I'm doing a reduction reaction, which is what I'm doing because I have negative current here. Now, one thing to note just about, and this is just random, it's just the molecules are moving back and forth, but I have a concentration profile that's starting to grow and develop. So this peak here is really, it's because, at this point, let me see if I can go right back to just around this peak. It's literally, I just don't have enough, like I have a low concentration of these molecules right at the electrode surface that are able to undergo the electron transfer. And they're all moving back and forth, back and forth, back and forth. But because some of these have been converted, they change, and so they're no longer near the electrode surface. That's why we get this this current, this peak, and then it continues to go down. It continues to decrease because I have very few molecules right here. I have a few more as I move away from the electrode, and these molecules here still diffuse back and forth, back and forth. But it's like the concentration is like the key, sort of say. So the random motion, I don't know if that's very helpful, Hobg. I think I just went into a whole thing about random motion, but I would say there's a somewhat predictability of the random motion statistically that allows us to get a reproducible cyclic voltammogram every single time, even though it's diffusion controlled. And that the peak current in the Randles-Sevcik equation does correspond to like, oh, this peak current. And there's a whole derivation of the Randles-Sevcik equation in actually Saviant's book. It's like dimensionless, whatever. But yeah, hopefully that kind of answers your question. It's like when you have trillions upon trillions of molecules, all of them moving back and forth bajillions of times, you end up getting these statistically significant and reproducible results, which is why these voltammograms show up reproducibly all the time. So something
it's relevant to go into a discussion about random motion when someone asks about diffusion.
That's true.
Just wanted to say what you did was perfectly reasonable because he asked about diffusion.
He asked about diffusion and random motion, which
that's what it is.
Which is what it is.
Hence,
yeah,
I had to change.
Don't cost it.
We've had some questions about diffusion, so I had to bring it back.
Yeah,
bring it back.
Yes.
Okay. We talked about diffusion, one better than the other. TT has a question about constant phase element in Warburg. So if we want to insert the values of the CPE and the Warburg open, both have 2 to 3 parameters. Well, they each have 2. Which one of these parameters actually expresses the element value? I don't really know what that means. And the other parameter value, should it be included too? Yes, it should be included probably, but I guess it depends on what you're trying to show or talk about. So for instance, just as a matter of definition, with a CPE, right? Q, we typically use Q or CPE. Sometimes you put the letters CPE in here, but typically it's Q. The impedance of my CPE is equal to 1 over j omega to the alpha times Q. Okay, and so Q is what we sort of think about as almost like non-ideal capacitance. Now it's tricky because if alpha is 0.5, it's actually like infinite plane diffusion, right? It defaults to a Warburg, but typically the CPE is used to explain or represent, model, let's say, capacitive elements that are behaving in a non-ideal fashion. And so alpha is sort of the these are English words. Non-ideality. That's another letter in the English language.
Yeah.
Non-ideality coefficient. Oh my gosh, this is the worst writing in the world. It's really bad.
You're on my scale now.
Yeah, this is Alex. This is Alex level of writing.
Yeah, just like the.
So what I tried to write here was alpha is roughly the non-ideality coefficient. That's what that's supposed to say. We're just gonna leave it there. I'm just gonna go with it. You can deal with my immense.
And we talked about it.
That's right, exactly. But alpha is usually between 0 and 1, and it's a degree to which your capacitive element, so to speak, is ideal or non-ideal. So if you're talking about including both of them, yeah, usually you do for just to, in a paper at a presentation, you'd say, well, my, Q is this value, and then it's, alpha was 0.9895, indicating, close to ideal behavior, or 0.7, so it's very non-ideal or whatever. With a Warburg open, it's a little more complex. The impedance of a Warburg, oh my gosh, W, it has 2 little, parts to it. Okay. So bad at drawing. My gosh.
It's okay.
So
it's hard.
So it's W over j omega. It's the square root times the cotangent of B. Should make these brackets because I have parentheses within brackets. times j omega to the 1/2 power. So don't worry too much about the math. I know hyperbolic cotangent, it's like whatever, and there's a imaginary figure to the square root power within a hyperbolic cotangent. The math gets a little hairy. Don't worry about it. The point here is that you have, again, two parameters. You have W, but now you have B. And so W, this is the Warburg constant, which is, as I showed before in my other slide, Warburg constant, right? It's basically proportionate to the diffusion coefficient. It's related to the impedance of the diffusion, and here you can see it's directly proportionate to ZW, right? B, on the other hand, B is equivalent to what's called delta over the square root of D. So D is the diffusion coefficient. So the diffusion properties, I guess you'd say, are related to both of these constants, W and B. For instance, the diffusion coefficient plays a role into B, but mainly what B is used as a measure of is this. It's the diffusion layer thickness. So if I have an electrode surface with a Warburg open, I have a diffusion layer, of some set thickness. This diffusion layer thickness is delta. And so if you're fitting with a Warburg open, I guess to the point of your question, if I'm understanding it properly, is like, well, would you report all these constants? Well, probably, because if you're getting a Warburg open fit, you have a B, and reporting the B value gives you some indication of the thickness of the diffusion layer. And if you're fitting a finite Warburg, you're probably interested in the diffusion layer thickness, because that's why you're fitting the Warburg open. Maybe. So it's reasonable that you would report those values, but those are the kind of the significance, I guess you'd say, of the parameters you get out of those two fitted elements in impedance data. So there you
go. Okay.
Some battery questions.
Yes. I think Ahmed is next. He says, "Hi, in lithium-ion cells, can the SEI be the rate-limiting step via lithium-ion diffusion? Is it similar to the double layer capacitance?"
No and yes. Those are the answers in order.
In order. Oh, okay.
So can it be the rate-limiting step? No. Is it similar to the double layer capacitance? Yes, absolutely. In fact, it is almost identical in function to the double layer capacitance. So there's kind of this odd phenomenon that we've discussed before, actually, you and I.
I need to remember it.
I know. I thought it through at one point when we were talking about this. This was like a year ago or 2 years ago at this point. It's been a while. We came to this following sentence that always trips me up, but I remember it because it's just a weird thing to say. Nothing happens until the double layer sets up. Nothing.
Right.
No charge.
Oh, yes.
No charge transfer happens. Literally nothing happens.
Yeah.
Like the world doesn't exist. There is no electrochemistry, period, until the double layer sets up. Yeah. Then everything can happen.
Yeah.
So there's a lot of thought that goes behind why that's true. It's a really cool thing to think through. I remember talking through this and realizing that, oh yeah, actually the double layer has to set up. And it happens really fast, it sets up really fast. That doesn't say anything about how thick it is, how much capacitance it has or whatever, but it sets up really fast when you have electrodes in solution, right? And then you can get charge transfer basically, but it cannot physically happen until the double layer has set up. I think it has to do with the impedance. The impedance is super low here. So then
it's kind of like the potential of the electrode is equal to the potential of the double layer. So if you're doing a reaction at a specific potential, that reaction will not happen until it reaches that potential.
Because electron transfer occurs through horizontally. That kind of is that part of that?
That's part of it. And here's the complication, because you often see this whole thing is, first off, this whole thing is super complicated.
It is.
But
and I'm going to relate it to the SEI in a moment, I promise. But this is a cool concept.
It's the so so let's say if, when you're doing CV, one thing that, people sometimes think is like, why don't I get a peak in a CV? Not a wave, not a nice like duck-shaped wave. Why don't I just get a peak that's associated with the E naught of my reaction? Like, why don't I get that? Why is it that I'm actually getting the electron transfer like at the foot of the wave, sort of say, as it, there's an onset potential where current is passing. But why do I get that? And it's because there's a distribution of energy states of your redox species that where it's thermodynamically possible for iron 2 plus to become iron 3 plus, or whatever the redox reaction is, because it's not like a gas phase thing. It actually has a density of states, a distribution of energy states. And as you charge the double layer, let's say you charge it to a very specific potential, as it's charging, you can get those redox reactions to occur. So as you're moving the voltage in a CV scan, you're moving it to a point where, like, okay, it's charged, so some current can go into the double layer, but that's also a potential where, hey, there's a state in the molecule that can undergo an electron transfer. So that's going to happen too. So I get a little bit of current due to that. So I get current that's non-Faradaic, charging the double layer, and Faradaic because there are molecules that are it's energetically favorable for the electron transfer to occur. And that's why you get this transition. It's not like, atomic what is it? Some, ionization energy where it's very discrete levels. It's like, no, there's a continuum, sort of say, of levels. And like, you got to charge the double layer to get to that level. But as it's charging to that level, it's also reaching energy states for an electron transfer to go. So that's kind of another like weird thing.
So what's interesting is that I don't know with certainty whether the solid electrolyte interface that occurs on a lithium-ion battery, for instance, operates with the same functionality as what you just described, where let's say the potential of the double layer is equal to the potential of the battery in this case, right? The potential of because it's also likely, and frankly must be the case in some manner, that there is also a double layer on a battery electrode. It's a electrode in solution. There's an SEI, and there could be double layer capacitance as well. That we get semicircles.
Yeah, get semicircles on the spot.
But I bring this up, and I kind of wanted you to explain that through a little as well. For the reason that there's a similar phenomenon, which is that in much in the same way that in standard solution phase electrochemistry, basically electron transfer cannot occur until the double layer has set up. Effectively, in a lithium-ion cell, discharge is not going to occur until the SEI sets up as well. It must set up. And the SEI is one of these really fun and baffling kinds of concepts, if you think about it, because it's like the one of the dangers of batteries is that you can decompose the electrolyte, causing thermal runaway. And the SEI protects against that kind of decomposition of the electrolyte by decomposing the electrolyte.
That's the next one. That's the next meme that we're gonna put.
Yeah. Yo, bro, yo, dog. I decomposed. Well, you have the SEI protects the SEI one actually.
Yeah,
I do. It's like, hey, I decomposed your electrolyte, so your electrolyte won't decompose. Now all your electrolytes decompose, bro.
Yeah,
or something. I don't know. But that is kind of what happens. It's weird. It's like a little bit of the electrolyte has to decompose to form this film, the SEI, that then subsequently protects and allows the charge discharge to occur, because otherwise the potentials at which you're charging and discharging in many cases is 3, 4, 5 volts or whatever. It's enough that it would rip the electrolyte apart preferentially, but the SEI protects against that. It effectively, you could think of it as like slowing the kinetics down to nothing, whatever, right? Of electrolyte decomposition, such that the favored process. So by that idea, no, it's not the rate limiting. So it's similar to the double layer capacitance, although it is a separate process. But no, it's not rate limiting, because it's the SEI formation happens, and then there's no rate. Like the SEI can there's other stuff that can happen with the SEI. It can thicken, it can collapse, like stuff can happen to the SEI. I'm not talking about maybe some of those secondary storage can occur. So I'm sort of talking separate from that. When you're doing battery charge discharge, typically the anode to the cathode reaction, it's typically the cathode, is considered the rate limiting step, because the SEI will set up initially, usually during the first charge discharge step, and then it's there. It's no longer rate limiting. In fact, there's no rate at all, and the decomposition of electrolyte isn't happening at all. It's not even part of it. So the processes that are occurring are now, and if you're doing impedance, you'll measure an impedance of the SEI because it's an interface, right? But it's not. It usually happens at the higher frequencies. It's a fast, it has a relatively, let's say, low, interfacial capacitance or whatever, interfacial impedance and everything. Sorry, my thing was flickering in and out.
Yeah.
I think we're still good.
Yeah.
It was just I was just adjusting the plug from my laptop. Sorry, just to put a pin in this, the charge and discharge processes that are happening at either the anode or the cathode, again, it's usually the cathode, which is the slower one, are much slower than the SEI just being there and nothing's happening. It's not setting up on every single charge discharge. It's always there, basically. So no, we wouldn't call it the rate limiting step. Although, again, it's sort of like semantics here. It's more of a language thing. You could say like, well, nothing happens until the SEI sets up. So you could say, in some sense, the whole battery is rate limited by the SEI happening in the first place. We don't think about it that way. Rate limiting is usually talking about the relative kinetic speeds or the heterogeneous rate constants of different reactions, let's say, right? And one with the smallest rate constant you'd say is rate limiting, something like that. And so we wouldn't really classify the SEI as being like a slow process that's keeping, rate limiting the battery, so to speak, I guess. So hopefully that kind of talks through that. All right. Next, I think Shijil had the next one.
He's asking, if I synthesize a material with very low porosity and one with extreme high porosity, how the diffusion will change. Can you plot the possible EIS spectra? Let's see. So one with high porosity, one with low porosity. There's a part. All right. Well, there's a part of me that like this is what I think would happen, but I don't know for sure. So
you might get a transmission line.
Oh, you may get a transmission line. Oh, okay. Because I was gonna say, I was thinking it would look something. My guess is like so this is what I'm imagining. I'm imagining you have your electrode.
Yeah.
And then you have some, porous film. Let's say this is the I don't know. Let's just call this. Let me draw both of them so that I have a better, I guess, idea. There we go. These are the size of the pore. So this is the. No, why is my computer
everything is a perfect sphere.
No, did my thing
did your thing crash?
No,
it's right there.
Oh, it did crash. It just
it's not sharing.
But let me share it. Because maybe I clicked
you're getting my undo problem.
I'm getting your undo problem.
Stop sharing thing. I don't know.
Close that. Yeah, maybe I clicked that. So review, or it just doesn't like circles or something. Could like that.
Doesn't like circles.
So this has let's see. So this is high porosity. I don't know. Maybe let's just call this high and let's call this low because there's fewer pores than this. So this is low. So my guess is if I was looking at, and I have like solution. There's just like solution. There's like redox reactions here, redox, and I've got redox. This is Z-real. Z-real, and then negative Z imaginary. And then I do that on the same thing, Z-real, negative Z imaginary. So I think if something has a high porosity and it's easy for electron transfer to go. Maybe you get an initial semicircle, and then you have some diffusional tail, but then it's a Warburg not open short, and then it curves down. And this is the same thing, but because it's high, it goes further, and then it curves down. That's my guess. I'm just saying that, like, this is lower impedance, this is higher impedance, but you get your diffusional tail, you still have this 45-degree angle, but at a certain point, it's like the frequency at with which you this process occurs is have a low frequency, and it's at such a low frequency, it's effectively as if it was a resistor, because it doesn't take long for the redox species to travel and go through this porous film, sort of say. That's how I think about it. I have no idea if this is correct, or if this is what you would expect to get. So
I'm trying to think that. So just looking at your pictures here, for example, if you have like two circles, porosity is defined as the volume fraction of electrolyte, effectively. So it's like if you have infinity circles, you have no porosity.
Okay. So
the porosity would be like zero. There'd be no, because if the circles are small enough, they fill every bit of space.
Right. So then it's a high resistance.
Well, not necessarily. No, there would be no diffusion at all.
There'd be no diffusion at all.
Right? Because there's no space for it to go.
Correct.
So actually, the way you drew it is right. Just the word high should be the word.
There should be low.
Should be the word low. You would have.
It should be high. Okay.
Hang on, I'm thinking this through.
Yeah.
So if there's no diffusion, you have. So the top is low porosity. Low is referring to porosity.
Yeah, low is referring to porosity.
But actually, what it's so actually, your Warburg stuff would be switched as well.
Yeah,
so the longer Warburg tail would be where there is higher impedance. The length of the 45-degree section is proportionate to the amount of impedance. So the top one.
Yes.
Step through this, right? This top one is low porosity.
Yeah.
Which means there's very poor diffusion, because there's not much space for it to go, right?
Yeah.
Low
spell porosity wrong.
It's POR.
POR. Yeah.
OS is no U's at all.
There's no U's?
No.
Oh my god.
Porous has a U, but porosity has no U's.
Okay.
POROSITOI. I think so. Yeah. So low porosity means that there's like no space for like liquid to move, right? So diffusion is very bad. Yeah. Slow, strained, whatever the word is, right? The diffusion is terrible.
Yeah.
Which means the impedance of the diffusion is high.
Yeah.
Which means that the length of the 45-degree line is very long.
It's very
long. It might still curl, it might still make a short, but there's going to be a long, long 45-degree line. Now on the bottom, high porosity, because there's the particles are large, so there's a larger volume fraction of empty space, which is electrolyte.
Yeah.
Whatever. So there's space for ions to move. Porosity is high. They can move a little more easily. The impedance is lower. The length of the 45-degree section is probably shorter.
So the length here is shorter.
That's right. W is smaller.
W is smaller. Okay, yes. W is smaller.
So that's my guess. Now, the only possible wrinkle here is that with porous electrodes, you sometimes get what's called a transmission line, which you could imagine looks just like what Alex is drawing here, except the first semicircle is not present. So it'd just be, it would just be like the Warburg short. It would just be like that.
Yeah.
And the length of which that first section would be proportionate to the porosity, the way we described. So the top one would have a long 45-degree section, and the bottom would have a very short 45-degree section before it curls, or just a lower impedance overall, is my guess. That's my guess.
Yeah.
That's our guess. We're not sure.
We don't know.
I don't have examples of high and lower porosity materials to check. There could be other things that would take an effect on this. For instance, things that are working against those assumptions, for instance, are the fact that smaller particles tend to have better electronic conductivity. And so, for example, while let's say diffusion or the Warburg impedance might be worse with low porosity, small particles, you might have better overall performance for whatever you're studying, because the small particles give you better electronic conductivity, better electron transfer within the material itself, even if the diffusion's poor within the diffusion is bad within the pores, the like kinetics is great. So there's other, there's more to take into account here. But as far as strictly looking at the diffusion with respect to those things, that might be what you would see. That's a good guess. That's a good way to kind of think it through.
Yeah. All right.
So Caleb is from LinkedIn.
Yeah, thanks for joining us.
Yeah, thanks for joining us on LinkedIn. So he says, in trying to recover metal using an electrochemical method, is CV the only method to recover metal? No. Or is other electrochemical to plate out metal? No, you'd probably want to use either constant current or constant potential, which would be called chronoamperometry or chronopotentiometry. So chronoamperometry, CA sometimes, chrono, time, amp, current, metry, measuring. So chronoamperometry is measuring current over time. So you're setting a potential, measuring the current over time. The other one, chronopotentiometry, CP, chrono, time, potential or voltage, metry, measuring. So measuring the potential over time. So that's when you set a current, measure the potential over time. Now, in a lot of cases, when you're recovering metal, so to speak, what you're doing is an electrochemical process, as you've noted here, to reduce or oxidize it. So if a metal is part of some other mixture, let's say, you might be interested in oxidizing it to make it ions that float into solution, or the other way. And then you'll collect the solution and then you have your ions or whatever of your metal. On the other hand, you could have it in ions in solution and you want to reduce those ions to make a plate. Like if you have copper ions in solution, you could put a platinum metal electrode into solution, put a reducing potential, and you'll get a film of copper to form. The copper ions will reduce to copper metal, solid, and then you've recovered the copper from your solution. Both of those involve setting the current or the potential, but let's just say setting the potential in a way that is either at an oxidation or a reduction potential to make that reaction occur. So CV would be a way to detect if you have the thing present or not, because you'll get a peak, for example, in many cases, indicative of the reaction of interest. But to collect it actually in some appreciable amount, you would probably do chronoamperometry or chronopotentiometry.
All right. Moving on. Ahmed has another question, again, about lithium-ion batteries. Do diffusion and migration typically oppose each other or contribute to flux in the same direction?
Well, diffusion is not going to contribute in any necessary direction because it is, again, as we've said, random. Diffusion will occur randomly in all at all times. I suppose in some situations they could, quote unquote, oppose each other just by happenstance. If the flux of species due to an electric field, which is charging or discharging or polarizing your cell to charge or discharge it, causes the flux of ions into or out of one of the electrodes, and diffusional randomness is also causing an ion simultaneously to have the chance that it moves in the other direction, they could oppose each other in some microscopic, like instance, like it's possible. But I don't know that we
I'm trying to think about like in batteries. I don't know, like in batteries, it's like there's so much material. It's like there's so much lithium that's moving. Compared to like a traditional 3 electrode cell and stuff like that. And I have no idea about migration in batteries. If there's a quote electric field inside the battery, that's, the potential is like pulling the positive or negative, the positive lithium ions in one direction or another direction. I don't know enough about that, like conceptually, to think about the direction and then like, oh, you have to add a bunch of energy, of course, to move them the other way.
Yeah.
I don't know enough about that actually.
Hmm.
Because it may also be the case that maybe they oppose each other, but one is so much more impactful than the other that it doesn't matter. That's also like, I don't know. That
Yeah.
might be another thing. So yeah, I'm sorry. I don't think I.
Yeah, I don't know that it's weird to think about them opposing each other. Again, I think that like if a flux is moving ions into the thing to charge, you know, like at some moment in time, there's a randomness of the ion moving away because it just happens to move that way.
Mhm.
Then they are technically at odds with each other. Like, I guess, you know what I mean? I'm just thinking in a very specific kind of abstract way. Like, I guess that could happen,
Yeah.
but it's kind of a weird way to think about it. Like, well, diffusion's working against it. Like, not really. They're separate
Yeah.
phenomena, right? Yeah. So,
Yeah.
anyway.
There is so Crunch X has a question. He removed one of his questions. His
Mhm.
first question retracted it, but these other questions, I have a test on electrochemistry. But I'm having trouble in Faraday's law. Like, I know the formula, but the concept is not clear. Is it talking about Faraday's law of electrolysis or
Yeah, that's
Faraday's
what I
law of
was
induction?
just looking up. I mean,
'Cause
I'm
I don't
trying
know
to figure
enough.
out like what form you're learning or looking at. Very generally speaking, Faraday's law is a way to, relate the mass of something and the charge to the number of electrons. Fair, because it's all based on Faraday's constant, right? I mean, you can sort of almost think it through just by thinking about Faraday's constant, which is and stoichiometry.
Yeah.
Like, I almost always just revert to stoichiometry and Faraday's constant, and then figure out how to calculate things just by what makes sense with units.
Mhm.
I kind of do it that way. Faraday's constant is 96 485.3, or give or take, coulombs per mole of electrons. So it's like in any reaction, A plus a number of electrons of B, let's say like 3A plus NE goes to 2B, then I'm just working on stoichiometry. So it's like if I know anything about how much of something I have or how much I made or whatever, then I can use Faraday's constant to get myself like I have like X moles of A, and I know that it takes 3 moles of A to, I should have put a number for N, but whatever, I'll just use N. Who cares? N moles of electrons, and then I have 96. Now I can use Faraday's constant. So I have 96485 coulombs per mole of electrons. So a mole of electrons cancel. So it's like how many moles gives me how much charge. And then if I have, like, or if you go the other way, you'd go from charge to moles, and then you can divide by formula weight and get the amount of mass. But it's like, if you have charge, I should have gone the other direction actually, because I think part of
Mm.
your comment was related to like, well, I have charge. How much stuff do I have or something? It's like, so it's like if I go the other way, I have like X, whatever moles of electrons, and it's like, okay, 96. Hang on, I'm putting it the right way. I should have put it in the numerator.
Oh yeah.
Yeah,
Coulombs per mole, and then you multiply by moles
yeah,
to figure out the charge.
yeah.
Or if you're measuring the amount of charge, then you would divide it so they can get the number of moles, and then you
Right.
can go moles to
Yeah.
some
So
mass.
what's missing here, I guess, is if you have charge. You didn't say you have charge. I know I'm kind of just making some random assumptions here. So yeah, so I have this. If you were working from the A, you would get to the electrons, and then you can get there. If you have already the amount of electrons, you can just use Faraday's constant to get you the number of coulombs, and then if you know how many coulombs of charge you have, that's how these are relating to each other. I don't know. I don't know if there's a better way to explain it. I usually just think it through as Faraday's constant itself. Really, I mean, again, Faraday's laws more broadly are charge versus what charge to coulombs and mass, I guess. I don't know,
Mhm.
very broadly speaking.
Yeah.
I don't know. I don't want to speak out of turn. I probably can't articulate them well enough here without like opening my textbook again. But
Mhm.
I don't know if you have anything more to say about that. I don't know.
No. If it's Faraday's law of induction, I don't know enough about that. I have to actually read about it, and I think it is more of just a unit conversion from coulombs of charge for the number of electrons transferred, and then relating that to the number of moles of a species in a redox reaction. But I think yeah, looking at the constant and then converting between them is the way to go. Don't know if that helps with the fundamental concept behind it, but it's just a conversion factor.
Yeah. It's just telling you how much charge is related to a mole of electrons.
Yeah.
And then stoichiometry tells you how many moles of electrons are related to how much moles of another material was made.
Yeah.
Right.
Yeah.
And then you can use its formula weight to get how much mass was made or whatever. So stuff like that.
Yeah. Well, let's not have any other questions about that or clarification.
Sorry, it's a bit scattered there, kind of talking through, textbook definitions here without a textbook in front of me. And I'm not a proper professor, so I probably didn't articulate
neither of us.
the best that I could. But if you have a more specific question, Crunch, please feel free to ask us. Okay, let's see. What is Aftermath software?
Yeah. I
have no idea. That's our company's software. So that's what we show, very often when Alex or I, show you guys
different
electrochemistry stuff. I just happen to have up for some reason the transmission line option. But so it's a electrochemistry software, circuit fitting, simulation.
It's used to control our potentiostats as well. You can do data analysis. You can use tools, export or import data for either circuit fitting or circuit simulation, as well as cyclic voltammetry simulation. And so
make notes about your experiment.
Yeah. So it's a whole like program package, sort of say. You can it's like if you purchase a potentiostat from Pine Research Instrumentation, it comes with Aftermath software that can be that's used to control the potentiostat. But because we also offer simulation options, we have a kind of a paid, very inexpensive license for simulation. If you want to either simulate cyclic voltammograms or fit EIS data, we have that kind of Aftermath has that kind of power to do that. So that's what Aftermath is. It's our company's software, and we use it
all the time.
Yeah, all the time, and especially during these live streams when we're trying to showcase something. It's very easy to show like, hey, how does the solution resistance change? How's the RCT? How does changing RCT change the Nyquist plot? We can easily show it in Aftermath software. So that's what it is. Yes. Tamogno said that he sent an email. So
I've got nothing yet. It might have got caught by our spam filter too. So if it got caught by our spam filter, Tamogno, unfortunately, we can only access that at certain time intervals. I know it's a bit weird, but which often with unknown to our to our internal server or whatever you want to say. Emails, they get briefly detained and questioned about their whereabouts, and then we tell the spam filter that it's okay. So it takes some time to get through the filter. So
it's a weird thing because the email address I sent you is like, it's a general email, so neither one of us have direct control over its spam filter.
It's one of the things about a mutual email address.
I'm
not an IT person, but for whatever reason it kind of functions in a way where everybody has access to it, but nobody really has administrative control very easily. So it's kind of a weird thing of working in a company like this. But anyway, once we get it, if we are able to look at it, maybe on a future live stream, we will.
There's a couple questions.
The diffusion in a battery is random. Well, the diffusion always is random. Again, that's definitional. Forced diffusion. So forced diffusion is called convection. It's not diffusion. So forced movement is convection. So so just as a terminological thing here, diffusion is random motion of molecules. That's what diffusion is not forced. Forced movement is called convection. So it's no longer diffusion. Just as a point of clarification.
Yeah.
Here. Diffusion is random in NMR. Diffusion is always random, no matter where it occurs, because it is definitionally random. So yes.
Yeah.
Here's a last question, perhaps. I think.
Yeah, because it is getting close to time.
Yeah. So is the RCT an intrinsic property of the material and the electrolyte it is in equilibrium with, or can we manipulate RCT by making it more conductive, or will it alter the RS value? RCT is a function of potential usually. So it is, I don't know if intrinsic is the right word. It is related to the material.
Yeah.
It's the charge transfer resistance. So it's the ease or difficulty with which electrons are transferred from your material for the reaction that it's doing, right? That is certainly a function of the material itself, but it is also a function of the potential, the driving force. The potential with respect to the thermodynamic potential at which said reaction occurs, which is called the overpotential, is the driving force for that electron transfer. And so the RCT is more closely a function of that potential. And so visually, we see that with the Nyquist plot, for instance, the width of a semicircle will decrease as you increase the overpotential, usually. Because you're increasing the overpotential, you're increasing the driving force for the reaction to occur. Therefore, you are decreasing the charge transfer resistance. Now, another material or a different electrolyte, or those things can affect the RCT as well. But in almost all cases, it's the applied potential at which you're conducting your redox process that will more heavily impact your measurement of RCT.
Yep. Yeah, that's right. It's like if you measure an RCT at the E naught, then you could call that like intrinsic to your material. But as you said, it changes as a function of potential. Then, it's unique in that way. But yeah, it changes as a function of potential.
Yes.
So that's good. That's good.
I think we'll call it there.
Yeah.
The usual caveats here, I guess, are our winning streak is coming to an end. So we will have probably 2 weeks off of this live stream, so everybody is aware. Anybody who's interested here, I will be traveling. I will be away, and Alex, you have your webinar series the next couple weeks. So if you want to see more of us for whatever crazy reason, you can watch Alex in the voltammetry series on the 11th and 18th of September. 2 time slots. You can register at pineresearch.com. Go to the webinars tab. Check that out. If you are in Germany at the International Society of Electrochemistry, or ISE meeting next week, I will be there. So I will see anybody who wants to stop by the Pine Research Equilibrium booth. Come say hi. And I will also be at the Italian Electrochemistry Conference the following week, the week of the something, 15th-ish. So, so I will be in Europe for the next couple of weeks, visiting some people and going to some conferences. So come say hi if you're there, and if not, then I don't care. So, but otherwise, we will probably meet you back here in a couple of weeks when we're both back in America, and wrapping up the voltammetry series and stuff. So, I guess until then, I hope everybody has a good couple of weeks, good weekend, good everything, and see everybody later.
Have a good one.
Bye-bye.